Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is however, it is time-consuming because it uses public key cryptography. So our work is to try to reduce the rekeying time cost in contributory key management schemes. Before going to our work, we first briefly review this two-party Diffie-Hellman protocol. Two persons, Alice and Bob, they come together. They want to establish a piece of secret among themselves. So Alice choose a secret key A, and Bob choose a secret key B. They agree upon an exponentiation-based G and a modular-based Q. And then Alice raised G to the A, and Bob raised G to the B. They exchange this information, and then they compute G to the power of AB by raising the received value to the power of their secret key. So in this case, Alice and Bob, they agreed upon a secret key, a group key, among these two users. Expanding this two-party Diffie-Hellman protocol, this protocol was proposed in '76, I believe. The recent works to extend this two-party Diffie-Hellman protocol to a group scenario, it's until the mid-90s. And we give a brief overview of tree-based contributory key management schemes. So in this case, a logical key tree is used to organize the keys belonging to the users. So this tree is a logical tree. It doesn't mean the network topology or anything. The leaf nodes correspond to the user's private keys. The root corresponds to the group key. And the inner node here corresponds to the subgroup key belonging to a subgroup of users. Those users are descendants of this inner node. So suppose three users come together, M1, M2, and M3. They try to establish a group key. M1 will first pair up with M2 and perform a two-party Diffie-Hellman. And then these two guys will act as one entity, the subgroup, to perform another two-party Diffie-Hellman with M3. So in this way, the group key is established. At some point, M4 tries to join. M4 will first find we call it insertion location in the key tree here. In this case, it's M3. M4 is paired with M3. Those two people, they exchange some information, perform a two-party Diffie-Hellman to form a subgroup key. And then these two subgroups, M1, M2, and M3, M4, they will perform another two-party Diffie-Hellman to update the group key. In the user departure case, suppose we have 5 members in the group right now, and then member M5 is leaving. Upon M5's departure, M4 will generate a piece of new secret key, a private key by itself. And then M4 uses this key to perform a two-party Diffie-Hellman with M3. After this, these two subgroups will perform another two-party Diffie-Hellman to update the group key. So this is the basic idea of the tree-based contributory key management. And the time cost here is the time cost during a user join or user departure event. So there are some time cost metrics. Usually people are using two-party Diffie-Hellman round as the basic time unit. So when they say how many rounds, it's referring to two-party Diffie-Hellman round. And a natural way is to look at one join event or one leave event. Another way is to look at average join time. We combine several join events. Average join time T join is just the number of rounds performed during n join events divided by this number of join events. Similarly, we can define average leave time. It's the number of rounds performed during n leave events divided by the number of events, leave events. Another metric is the overall weighted average operation time. this T is the weighted average between T join and T leave, where this big N is the summation of N join and N leave. So you can see this as number of rounds, also number of rounds divided by number of events. So why this time efficiency is important? It actually comes down to two perspectives. First, from the user's perspective, during the user join and the user leave key update, the user has to wait. So this is related to user satisfaction of the group application. Another perspective is to view this group as a whole. Suppose the group leader tries to deploy some task to other group members. And then before the group task cannot be deployed before the group key is securely established or updated. So if we can establish or update the key faster, there's a better chance we can deploy the tasks more successfully. And contributory key management schemes, they employ two-party Diffie-Hellman, and each round is time-consuming. Some results of the existing schemes, like group Diffie-Hellman by Steiner and tree-based group Diffie-Hellman by Kim, they can achieve a time complexity of big O of n, or big O of log n, where this n is the group size. This motivates us to consider the following question. Can we do better than the current tree-based schemes? So with this motivation in mind, we propose another topology to manage the group keys. We propose this joint access tree topology. This key tree here consists of three parts. It has main tree, the exit tree, and the join tree. The join tree and the exit trees are just small key trees closer to the root of the key tree. And they serve as temporary buffers for the joining users and leaving users. We define join tree capacity C sub j and the exit tree capacity C sub e as the maximum number of users that the join tree or exit tree can hold. So the basic idea is like the memory hierarchy in computer architecture. When the user tries to join the group, those users will first be added into the join tree. Later on, when the join tree is full, they are relocated together into the main tree. At the same time, we identify those users that are going to leave in the near future. We move them in batch into the exit tree. When those users are leaving from the exit tree, it saves some time because the exit tree has a smaller depth than the main tree. This is the basic idea. And the details are picturized in this figure. The join tree algorithm consists of four parts. First, we try to determine where is the insertion location in the join tree if the user is added to the join tree first. And then the second question is, how do we do this join tree relocation? The third question, this is also the most important one, I think. What is a good join tree capacity? Because intuitively, let me go back one slide. If the join tree is too big, it's not good because it will be similar in size as the main tree. Our purpose is not to use a very big join tree. If it's too small, it's also not good because in that way, we cannot achieve a batch effect when we do this relocation. So we need to, this is a trade-off. We need to determine a good join tree capacity. Also, our goal is to reduce the average join time and average leave time. So with this goal in mind, when shall we use the join tree? And under what condition can we use the join tree to reduce the average join and leave, average join time? Similarly, the exit tree consists of three parts. First one is the user departure from the exit tree and batch movement. How do we move users from the main tree into the exit tree together? And under what condition do we move those users? And we need to determine exit tree capacity and the activation condition of the exit tree. So we go with the insertion strategy first. Here we give a pictorial look of the insertion strategy. We show the join tree only, and suppose the join tree capacity is 8. When the first member tries to join, it naturally becomes the root. M1 becomes the root of the join tree. And then M2 joins. M2 is paired with M1. When M3 joins, since M1 and M2 already forms a balanced subtree, so M3 is inserted into the root of the join tree. M4 is paired with M3. And then when this part becomes a full balanced subtree, M5 is again inserted into the root of the join tree. So in this way, we can systematically grow a balanced key tree. And we also note that according to this pattern, the kth user inserted into the join tree, the time for the kth user is RK round. It's a sequence, special sequence with some special properties. If you look at this special sequence, the first two, we move them to the second two and then add up by 1. It's just the third and the fourth is just the adding 1 to the first two. And then if we look at the first 4, we move them, shift them to the next 4, and add by 1. The 5th to the 8th round time cost is just those things add by 1. So on and so forth. This sequence has some special property, and this property can be used later to determine the join tree capacity. So now we specify the join tree location process. Suppose the join tree is here. We break the join tree from the root. This is just by computing another Diffie-Hellman. Just remove this part. And then we break a part of the main tree similar in size as the join tree. We merge them together using two-party Diffie-Hellman. And then we update all the keys on this branch all the way to the root. So in this relocation process, the time cost is log of n sub n, where the n sub n is the number of users in the main tree. So having the relocation process and the insertion process in mind, we can try to determine a join tree capacity. We consider a sequence of n, small n join events, where this n is also the join tree capacity. After n join events, we perform a batch relocation. So the average join time in this inequality consists of two parts. The first part is the sequential join at the join tree. It's a summation of the sequential join time cost. And yes?
Why do you say that the cost is logarithmic? It's true that you have to go up in the logarithmic cost, but then you have to let everybody that was affected have to step down back, and the spread will be wider than originally.
Yeah. Let me go back to this one. In all the existing works, the assumption is like this. First go back. No. So when they perform this, it will spread out to these people. And then the assumption is these people are synchronized. These are done in parallel. So the time cost is computing it in parallel. They can compute at the same time. So the sequential join cost is here, and the relocation time cost is log of n sub n. And we can show by the special property of that sequence, this sequential join time divided by the number of join events is upper bounded by half of log small n plus 1. So therefore, the average join time is also bounded by this inequality. So here we do an approximation. We minimize this upper bound. We also relax this integer constraint on this small n to a continuous variable. So the join tree capacity C sub j is chosen as the argument minimum of the upper bound, rounded to the nearest integer. We use this square bracket to represent the rounding operation. So C sub j equals to twice natural log of n. And according to this equation, we can determine the capacity relation of the join tree and the main tree. So the join tree capacity is at the log scale of the main tree size. This is the first direct result. A second indirect result is that the depth of the join tree is at the log scale of the main tree size. And when the user number, the group size grows to bigger and bigger, this depth of the join tree will dominate the average join time. We'll show it in the next slide. So we substitute this value into the upper bound here and compute an upper bound on the average join time. The average join time is bounded by this value, where we can see clearly it consists of two parts. This is a constant, and this is the part that grows with the group size. So this part grows with the group size. The asymptotic join time, average join time, therefore, is bounded by log of the group size. After this, we specify an activation condition for the join tree. Let me go back. Yes. Yeah, NM. NM. NM is the number of users in the main tree. NM is the number of users here in the main tree. Yeah, I use the big N because this part is always smaller than the entire group size. So since it's the upper bound, I use I change to that big N. And then we try to determine the activation condition. The activation condition here. Oh, let me again go back to see here. The join tree, before we have this complicated structure, we have only this kind of structure. It's a balanced tree, main tree here. And the join tree adds some overhead to the entire structure. So it's intuitively, when the group is large, using the join tree will give us some gain in the average join time. So we try to determine how large is the group size at that threshold group size to activate the join tree. And by some mathematical manipulation, also on that upper bound, we can derive this. When the group size is larger than 8, using a join tree will reduce the average join time compared to a simple key tree. So we compare two cases. One is without employing the join tree. The other is using the join tree. We'll compare the average join time of these two cases and see at which how large is sufficient. How large a group is sufficiently large to get some gain, to reduce the average join time by employing this join tree. So this is the activation condition. I didn't put the details here.
So what's the intuition behind this constant number and it's independent of everything?
Yeah, it's independent of everything. You mean how large is this one?
No, I mean like you just come up with a magical number 8. So
this 8. Intuition is like this. Okay. Intuition is like this. Now we have two parts, this sequential join and the relocation. We compare this value, the average join time, with those using a simple key tree. It only has a log term. It only has a log term. So we compare those two. The log term also has the group size in it. Here we have roughly the group size in here. So it's actually just solving an inequality and then to find a integer number as its threshold. So it goes down to 8. Yeah.
So you have to propagate back.
Yeah.
The whole tree. So when you join the first node,
yeah.
have the first node and the join tree.
Yeah.
You still have to propagate that the other way back, otherwise.
Let's still go back here. Okay. You mean, say like this one is joining?
So you have 3 joins.
M3 is joining. Okay.
So you do a Diffie-Hellman.
Do a Diffie-Hellman. Say, suppose M1 is doing the Diffie-Hellman with M3. Actually, they need to send something to M3, right? Either one is okay to send the piece of information to M3. And then M3 multicast a piece of information to these two guys. And these two guys, they just compute by themselves. They compute by themselves simultaneously.
Yeah. But then, what I'm saying is, suppose on the 3 on N1 and 2 is the actual problem.
Yeah.
So, in that case, don't you have to propagate back?
Suppose like this. Someone is here, joining here. And then, suppose we don't have this axis tree. This part, we view it as the same group. They act as one person, or one of them send a message to this guy, and this guy multicasts a message to all the members in this main tree. So this is they receive the message together, they compute together. So in terms of the time cost, it's roughly the same because they're all computing the same thing. Okay, then we finish the join tree part. Now we go to the axis tree part. Here we have an assumption. We assume the users, they have an idea how long they are going to stay in this group communication scenario. So we identify those users that are going to leave in the nearest future. Those users, we break them from the main tree and move them into the axis tree. This breaking part is just some cryptographic operations. And here, those users are paired with the axis tree users. And then we mark all the keys on these paths, and on the paths in the axis tree, and also on this path. The orange path are the marked path. Those are the paths. The keys on this path are updated after this relocation. The batch, we call it batch movement, actually, in this move case. So we want to determine how many users are moved together. We call this batch movement size B, and we want to determine a condition for the batch movement. So here is the proposed batch movement condition: U sub C smaller than rho U sub P. So where this U sub C is the number of users, current number of users in the axis tree. This U sub P is the number of users in the axis tree after the last batch movement. And the rho is a parameter, the system parameter between 0 and 1 we decide. So at the beginning, the axis tree is empty. There's no user in it. We move B users into the axis tree. And then those users are leaving from the axis tree. So the number of users in the axis tree decrease until it decreases below a threshold. Another B users are moved to the axis tree. So it grows like this as an exponential number series. And it converges to this value, B over 1 minus rho. So the relation of this axis tree capacity and the batch movement size is C sub E equals to B over 1 minus rho. So in this system, we have 3 parameters, but actually we only have 2 because determining 2, we can determine the third one. The rho is the one that we choose beforehand. We will later on see, we will determine this C sub E and B according to the number of users in the main tree, like we did in the join tree scenario. So we consider, to determine the axis tree capacity, CE, or the speed, those two are equivalent. We consider a batch movement of B users. This is just some notation change to make it more clear. We want to do some optimization or some derivation here. Suppose the axis tree capacity is related to this B, as we have seen in the last slide. This average leave time is bounded. This is a similar trick as we did in the join tree case. It's bounded by this value. Why? Because there are 2 parts. This is the batch movement part. We move the users together from the main tree to the axis tree. And this part is the users leaving one by one from the exit tree out of the group. So there are two parts. And divided by this B, leave events. So this is an upper bound for this average leave time. We minimize over this upper bound here to get C sub E, or this B. The exit tree capacity is chosen as the argument minimum of this upper bound rounded to the nearest integer. It's also at the natural log scale of the group of n sub n, divided by a factor. However, this B, if we go back to last slide, this B equals to C multiplied by this factor. This B is not related to this row, so it's only determined by this group size. The batch movement size is only determined by this group size. So in this case, we have determined C sub E and B. So where does this row comes into the picture? Here is, okay, let me go back one slide. Our assumption here is we know when users are going to leave, and we can estimate this thing quite accurately. Suppose we cannot. What if we cannot? Some users are moved to the exit tree, and because they reported an inaccurate staying time, they are going to stay here longer than expected. So they are not going to leave. Since they occupy this part, no other users can join the exit tree because it's already full. We have a capacity upper bound on this exit tree. So there's no room for other guys to come in. So this row comes into the picture because by dividing this factor, C sub E is actually larger than this B, makes more room for this inaccurate estimation of staying time. So this is our goal, to have this parameter in the system. You mean, I didn't get your question.
Except putting an upper bound on
yeah.
the absolute upper bound, they have to keep the average as well.
No, I'm putting a absolute upper bound. This is an absolute upper bound. The average.
Some kind of average or amount of working.
I'm not considering. Yeah, no. I'm not considering this. Yeah, all these things are deterministic. So only the average time. Also, this average time is also a deterministic average time. It's not the statistical sense or average the average sense. So by substituting this C sub E into this upper bound, we can see the average leave time is also bounded by this thing. It's a constant part plus a part grows with the group size. And again, it's the log-log scale of the group size. Similarly, we determine an activation condition for the exit tree. Whenever the group size is larger than 256, this number is much, much larger than the join tree case. That's 8, if we remember. Then this is a threshold group size to use the exit tree. Let me explain this a little bit why. So it seems this is much larger than the join tree capacity. No, the join tree activation condition. Okay, let me explain from here. Adding the join tree to the key tree, this is we call it structure overhead because we have one more layer, one more level here. Adding an exit tree, we add another layer. This is another depth. And then the number of users in the main tree will grow exponentially. Although that's by 1 or by 2, the users down here grows exponentially. So that's why the activation condition for the exit tree, when we compare this complicated structure to the main tree only, the threshold group size is much larger than the case of join tree only. Okay, that's pretty much the scheme, and let's see some simulation results. The first one is on sequential user join. in this case, we consider user joining a group one by one. There's no user departure involved. And we plot this performance. The horizontal axis is the group size. The vertical axis is the average join time. We plot the performance of our jet scheme. This is the blue cross, and the tree-based group Diffie-Hellman, TGDH. This is the circle. And the analytical upper bound for average join time we have shown before using this red dash. And we can see that this horizontal axis is in the log scale. So from this trend, our scheme actually achieves a log-log performance. And the TGDH achieves a log performance. This upper bound holds very well for our scheme.
This upper bound is not asymptotic effect, is it?
This upper bound is not. It's not. It's for each group size. The upper bound is strict. Yeah. And the second experiment, we use MBone data. This multicast backbone, there are some, maybe during the 90s, are still carrying on right now, I think. I think in our school, just one floor up on my office in the CS department, they can still access this MBone. I don't know. Yeah, I have some friends told me this. I don't know. We collect this data from the existing MBone data from the internet.
I'm sorry, what is this MBone?
This is an experiment carried out during the 90s. Many universities, are there any research institutes? I don't know. Many universities, they form as a multicast group. There is a overlaid multicast. It's actually not actual multicast. It's overlaid multicast on the existing internet. And then they form this to experiment the multicast, to simulate the multicast operations and the applications. So some server will run at one school, and all the other guys in other school can join the application in that server. Or some company will run something there, or broadcast or multicast something there. So I think it still exists. No, they are not using them anymore, but it is the infrastructure is still there, right? I think this is the most active in the mid-90s. Oh, yeah. Most are universities, like UC, Berkeley, Maryland, some other schools. So there are some existing data, the multicast data. We choose 3 sessions. 2 sessions are NASA Space Shuttle program. Another is the CBC News World Online. So we can actually plot this user activity. These are real data. People are joining this group and leaving this group. The horizontal axis is the time unit in minutes. Is that in minutes? No. Let me think. No, it's in second. It's in second. Yeah, it's in second. Otherwise, it will be too large. This one is the number of users currently in the group. This one is the number of users at the moment joining the group. This is the number of users leaving the group. So it can be plotted like this. This is people are coming, people are also. So this sometimes are active. Maybe this is at night. This is during the daytime, or they just after dinner they have some free time to join. Graduate students.
The characteristics of the people entering and leaving are very, very similar. It sounds like that. It looks like that. Maybe it is like that. I don't know. Yeah. Starting week at 7,000. Maybe it's the beginning of the night shift or something.
There are actually paper about this MBone user behavior and how to use statistical model to model this MBone user behavior. The result is like this. There are several observations. Why they are doing that? The peak appears at the same time because some users are joining, and then after 5 minutes they just leave. So that's why you see that the peaks are almost at the same synchronized for join and leave. Another thing is the traditional queuing model can be applied to the user activities here. the Poisson arrival rate and the exponential staying service time, in this case, the staying time. So we simulate these 3 sessions using MBone data, and we compare the performance of our scheme to those of the TGDH. This TGDH is a very typical tree-based Diffie-Hellman, the grouped key management scheme. So in the average join time, we can see that we achieve a reduction of more than 50% in the average join time. In the average leave time, we also achieve some gain. However, this gain is not the result of using the exit tree. Because if we see the group size is smaller than 100, the typical group size is around 100, smaller than 200, the MBone data. And I haven't seen anything beyond 200. So the exit tree hasn't been activated yet, according to our protocol. However, because of this special user activity pattern, they join and leave almost simultaneously, we can say. They join at the join tree and they leave also from the join tree without a trip to the main tree. So because of the special pattern, we reduce some average leave time by using the join tree only in this simulation.
So this means that you actually need to come up, based on the practical data, you need to come up with a threshold which is less than 2 things.
Yeah,
right?
yeah, I need to come up with a threshold.
So something, there is a mismatch somewhere, probably.
Yeah. This one, the first one, right?
So what is the cost? So I have the impression that you don't gain anything.
Yeah, I don't get anything for the small group size.
Yeah, but what are those numbers?
The group size. Oh, here it's too small. This is 10. It's roughly say like 12. No, not 12. 20.
It's like 50.
Uh,
Around 50.
30 or 30, 40. I don't get anything. Maybe smaller than 50. I think I remember it's smaller than 50.
But then the group of that size isn't exactly smaller than 50.
MBone. This is just one of those things.
So the group size are like 20. So you shouldn't have any gains.
This is the sequential. This is only considered a user join, sequential user join. User join one by one, and then they don't leave. They just stay in the group. In this case, there are user join, there are user leave. There are many changes. Let me try to explain this better. Yeah, I think this is a combined user activity, and it makes things more complicated. There's some pattern you cannot predict when the user is going to leave from where. So that's why you can see there are some gain here. Also, that's okay. Yeah. I didn't show you the other two MBone sessions. The group size is much bigger than this one.
So are your results?
Yeah.
In the next slide, yeah, are the results sort of like aggregate results, meaning based on the all MBone data? You said that there are some MBone data also for which the user numbers are very, very big, rather than very.
Let me see.
No, you don't need to show. I'm just asking. Are these plots based on those aggregate results?
Not aggregate. I tried to say 10 something below 20 20 sessions, about 20 sessions. I can get gains on all those things, and I just randomly pick 3 of them here. This is not aggregate result. But
not these plots, the bar plots. The
bar
graphs that you show.
Yeah.
Are they based on the average gains, or only one of them?
Average. It's average. It's
Okay.
average.
Okay.
Average. Average. So, since we don't have that big group to show our exit tree performance, we simulate a group communication scenario where the arrival time is modeled as a Poisson process with mean arrival rate lambda, and the staying time is mu. There are 5,000 total time units, and we divide it into 4 segments. Each segment has a different arrival rate and average staying time. So here we need to estimate the staying time. We have the assumption like this. Each user they report their estimated staying time with probability P1, or they do not report with probability P0. We want to see what is the performance of the join tree and the exit tree if we don't have that much reported estimation time. If it's reported, we assume it's accurate. And the residual rate is set to 0.5. This is a heuristic value. I get this from some experiment.
I thought that was the number of nodes rather than an egg.
This one? No, this residual rate is used in the exit tree to determine the exit tree capacity. If you remember, each time we move B users, and the exit tree capacity is related to this B by this residual rate, B divided by a factor 1 minus rho. So, okay, let me illustrate this. If we have exact information, what we will do? We move these B users to the exit tree, right? Since we have exact information, before they leave, nobody else will leave. Is that right? So we just wait for all of them leaving from the group. And then we move another B users. So there's no need to make an exit tree bigger than this B. Is that right? Right? That's right. So however, if we don't have exact information, we move these B users into the exit tree. And then some of them are leaving. Some guy here is also leaving. So this exit tree, some users are staying here for quite a long time. It holds the position here. Nobody else can come into here. So that's why we want to make the exit tree capacity bigger than the number of users we're moving to the exit tree. Yeah. This is an assumption here. Yeah. You mean this one? Yeah. The assumption.
When the report's going to remove the tree, if the information is accurate, then you don't need code, right?
No, the reported time is before they actually are going to leave. They report sometime prior to their departure. They either report, say, upon their arrival, or report sometime after their arrival, but it should be a period of time before they actually leave the group. Otherwise, there is no time to manage to coordinate this leaving process.
No, I still don't get it.
Okay.
What I didn't get is, to assume that's active,
Yeah.
then there is no reason anyone would ever be left in the exit. Does it not put it there, allow it to report?
Yeah, that's good. That's right. There's no need to set this one. Yeah, it can set to say 0. It's like 0. Nobody is there. When nobody is there, we move another batch of people into the exit.
So you can put it at cat just because you're assuming that you have to be activated to report exactly just to simplify your computation.
No. Because these are our assumption, but in the scheme we don't know this. Suppose we don't know this assumption here. So because we don't know, we are trying to test different scenario, and the scheme is still fixed. How does it perform in different scenario? So we plot the performance here. So this is the probability a user will not report, and it goes from 0 to 1. So at this end, nobody is reporting. The TGDH performance is like this. And this is the performance for our scheme, the JET scheme. The blue line is the average join time. This one is the average leave time, the green one. The red one is the weighted average, overall average. So the average join time is much smaller than this one. The average leave time, when there are, say, 80% of users not reporting, it's worse than this one. the overall average is always better than this one. The overall average of this TGDH is about 10.5, by the way. I didn't calculate, because the join and leave events are almost the same, the number of events.
Why would you expect that you use this collection? Use the report of capacity?
Because this is from a real scenario. Like if I'm going to attend a video conference, or I'm going to make a conference call to somebody else, say like in New York, LA, San Francisco.
Not when I'm reading a website.
No.
CBS morning news is not one of them.
No, CBS. Maybe I will come and see it's not interesting. I will just go. But that's for the teleconferencing scenario. This is
Is there any case in your application where you have like thousands of users, and then one of them needs to change?
yeah, I would say the first one I can imagine is Battlefield, and because that's the most important. Yeah, that's the most important. Sometimes the user leave, or sometimes we call it revocation. The group just kick him out.
They will like, especially electronic payments. Nothing is, I do not know anything is so big that it is running, and people always talk about this.
Another one is, say, in the sensor network, supposedly we deploy thousands of sensors somewhere here and there, and those information collected are confidential. And sometimes a device got tampered by adversary. Yep. So, I'll explain here a little bit the last data point. The last data point is because at this moment we are still using the exit tree, and the exit tree is an overhead. At this point, nobody is reporting, and it's not used. So we get a dip here at the end. Okay. Now we consider the report accuracy, not report, and we will consider another one, reporting inaccurately. So we consider three classes of users. The first class report accurately. The second class not reporting. The third class report according to a Gaussian distribution, mu and sigma. This mu is the actual staying time. This sigma is the deviation. It's proportional to its mu, and the ratio is R. This R is fixed for all the members in the third class. So this is some assumption in the simulation. We try to test the performance of schemes. And the settings are, we fix this R at different 0.1, 2, 3, and there are no users without report. All of those users are reporting in the following simulation. So, and we vary this P1 between 0 and 1. Basically, some users are not reporting inaccurately. Some users are reporting accurately. So we plot the performance here again. This is the proportion or probability a user is reporting inaccurately, the EST, estimated staying time. And these lines are for different R values. Here, these three lines. There are three group of lines. We see a similar trend as in the last simulation. And what we can see is those average time actually saturate when the proportion of users not reporting inaccurately increase. And another observation is that the average join and average leave time average join and weighted overall average time is always better than the existing schemes. However, because this exit tree performance is sensitive to the users, the accuracy of the users reported staying time, we see some changes. The slope becomes deeper and deeper when this reported staying time is more and more inaccurate. So this becomes more and more sensitive to the inaccuracy here.
The interesting thing is, in the previous plot, you had some non-monotonic behavior to go on slide, right? when you were pressing in enough.
Here.
From 0.9 to 1. So intuitively, I mean, every joint time, not joint time, which leave time, which overall time, of course. Intuitively, it should be monotonic with respect to enough. So that's why the second thought makes more sense, right? I mean, why are we seeing a non-monotonic behavior here? I mean, the other one is monotonic, this one is not monotonic. It's kind of interesting, right?
You mean
Yeah.
the last point? Last point. Okay. This is because they either report accurately or they do not report. And in this case, all of them are reporting just some. So the exit tree is always used. And as long as their users reporting their staying time, the exit tree is used. I mean, and the group size is large enough, the exit tree is used. So this non-monotonic point is because when there are no users reporting, the exit tree is totally. Okay. So we studied lots of things. This is the last one. The last one is all the people are reporting inaccurately. So all of those are not honest. And the deviation, the inaccuracy in their reported staying time changes. These R changes between 0 and 1. So we plot this one. You can see in this case, we still get the same trend as in the, so we see different parameters, but with very different parameters. So we always get the same trend. However, this average leave time is more sensitive because this horizontal axis is R in log scale, and this vertical axis is the average operation time, and this part, when this R is smaller than 2 to the power of minus 2, 10 to the power of minus 2, we get something. This kind of inaccuracy can just be ignored. We get the same result. When when R becomes larger and larger, the average leave time grows very fast. The average join time doesn't grow, doesn't change that much. There are too many parameters. R is a parameter we describe the inaccuracy, the deviation in their reported staying time. A user, remember, the reported staying time is a Gaussian random variable. The mean is the actual staying time. The variance or the standard deviation is proportional to this mean. So that's.
So why is it that the accuracy of the
This is because in the actual protocol we implemented, whenever the user, because it's not accurate, some user will leave from the main tree. Whenever this user is leaving from the main tree, and there are also users in the join tree, we do those two things together. Yeah. Yeah. Then, and this is just a counting, toward this end or towards that end. So it doesn't matter actually. Okay. So the conclusion is, we propose a jet scheme consists of 3 parts: the topology first, and then we derive some capacities. Also, we design some activation and updating algorithm for this scheme. We achieve a lower time cost, and thus it scales better when the group size is large. Okay, that's all. Thank you.
So I have a question. So if you go to the very, very early slides, when you were drawing the trees, both the joint and exit tree, you were doing first something very intuitive, which is drawing the trees in such a way that you are, I'm not sure. Anyway, so you are drawing the trees such that you are always trying to minimize the depth of the tree, right? So how do you draw these trees, joint tree and exit tree? You always minimize the depth of the tree.
Always make it as balanced as possible. I mean, if there is some vacancy in the here, I will, and there are also users down here, I will first plug in the vacancy so that it can be balanced in the join tree and exit tree.
So is that the best thing to do regarding your first
Actually, this is not my invention or my strategy. So before that, I mean, there are many papers on this key management, like tree-based. They don't have this topology. They only have this tree, and they said if you do an unbalanced tree, it may be beneficial to a particular event, either join or leave. But when you consider the combined events, overall the performance will degrade. So they suggest to use the strategy to make it as balanced as possible. So that's based on heuristics. And I think our contribution is to propose this structure, this new topology. But inside here, we don't have that derivations or mathematical validations for, say, where to insert this user or where to let the user leave or where to insert the user into the exit tree. We still don't have that mathematical derivation here.
Because intuitively it sounds like that kind of drawing essentially optimizes the worst case scenario.
Yeah.
They're balanced everywhere.
Yeah.
But if you have some statistical belief, which of course you are not addressing here, you are proposing a deterministic algorithm. But if you have some statistical belief, then presumably you can come up with different populations or different algorithms.
Right. Especially if the users can be classified, say a part of users has say average staying time longer according to a certain distribution. Another part of users can be classified as say short staying users. Those two parts can be separated, and then those two parts will not say intervene with each other. They will not fight for the join or leave location. So this requires some prior knowledge of the user's behavior, right? Yeah, and I think there might be existing works in this direction. I probably have seen one or two, maybe one.
So what do you think about further improvements, further research on this work, or is it none? I mean, not the field, but as far as you are concerned.
Yeah. Okay. Let me say this. I think there are a few places I can improve a little bit, but the main structure, I feel this is done last year, 7 or 8 months ago. Like, I have considered this a lot. I feel it's hard to have much better, a big gain from here. Maybe after several years, there will be other ideas, good ideas come out. The one improvement is here. Let me show you this. One improvement is here. We are minimizing the upper bound because this part is mathematically tractable. Directly minimizing this, you need to do an exhaustive search in this case, because this RK, this summation cannot be written in a closed form. It can be written as a combinatorial thing, but it's hard to derive this CJ. So one thing we have done, actually another postdoc in the group with Dr. Liu, if you know, he has a math PhD, so he did this. He derived this exact combinatorial form, and he used exhaustive search for a set of group sizes that are exponential. Oh, I forgot to mention, this inequality is tight. This is equation when this n is a power of 2. So he derived those things at the power of 2, and then we want to make a table. For those in between, we just use the nearest one. So if we pick, say, sometimes we pick 5, but actually the best integer value for this C sub j is 7. The performance gap is 10% from the current simulation results. It's 10%. The derivation results, not simulation results. So we want to see whether using the exhaustive search we can get some gain, but that's maybe 10%, 5% performance gain. Compared to the current one, we have maybe 50%, 60% with the existing scheme.
It's not worth solving combinatorial problem in this case.
And the other one is the one you mentioned, to use the statistical models to model the user's behavior, like the Poisson process. This is also another thought we have discussed in the group, actually. It's an interesting direction. We try to, here the capacity is derived using this deterministic upper bound. We try not to use this upper bound, these equations. We try to use the statistical model to model the user joining the departure behavior, the average user. Okay, at a certain time, how many users are expected to leave? Like this, using that kind of information to derive this capacity. Still using the same topology, but the parameters are derived differently. So if we know some prior information of the users, probably we can get a better result than the current one.
So join tree.
Yeah.
Why do you need a tree? Why don't you use like a linear?
Yeah. Okay. Let me. I have a backup slide for this one. Let me show you. I was expecting.
Looks like someone asked the question before.
I was expecting this one. I'm sorry. Should do this. The group Diffie-Hellman protocol proposed in 1995, 96. They use this. All the users are lined up in the. This we call it a queue or something. They start from the first one, send something to the second one, then to the third one, all the way go to the last one, and then it propagates back to all the users. So in this case, if we consider the time efficiency, it's a sequential operation. So it's much slower. This is the first case. The second case is the storage. Everyone needs to, in this scheme, the n-1, this user needs to store all the keys or some variations of the keys of those users before it. In the tree, the storage is at a log scale for each node in the tree. If we,
I mean, I assume storage is not a problem.
storage is not a problem.
You never, you're most worried with time, right?
This is the time. The time storage and I would say.
So it's linear, the time is linear, but if you're joining one at a time, then it's just one, the time is one.
Yeah, right. If you join one at here, it's just one. You need to go further one step back and propagate back.
Yeah.
However, when some user tries to leave, it's very problematic.
So there's the leave part.
Yeah.
Right?
Yeah.
So when you have to leave, then you reassign that, you redesign that code.
Then it's another ON process for the time efficiency. You redo all the entire. The current scheme is when this guy leave, from here to the end, we do this half circle. So the expected leave time is half, n over 2. The expected, statistical average is the n over 2.
When the guy leaves, you forget that you had the tree. So if someone from the join tree leaves, the join tree is not a tree, it's leaving.
Yeah. Okay.
If someone from that linear part, the main tree is still a tree.
Yeah.
If someone from the join tree leaves, you just forget that guy has to leave.
Mm-hmm.
And then now you make the whole n-1 that were in the join tree. You now create a tree and put the name. In other words, you merge part.
This is a paper we are writing right now. Okay. Well, we actually are trying to explore this idea, and this is one of the ideas. And there's one thing we don't know is if we. I know the idea is using this main tree, and this is a straight line here. And when someone is leaving from here, those guys are relocated into this place, right? This is the idea that we had not recently, a couple of months ago. And because this is only an idea on this join and the relocation part, there are also leaving part from, if we are leaving from the main tree, what can we do? So we're considering many aspects. Yeah.
Every time someone leaves, doesn't matter if actually you're drawing on the game. And you actually have to do a lot of operations in the main tree. So at the same time, you're drawing. You put forever was in the drawing tree.
Because in that idea, the join tree can grow arbitrarily. I would say it can grow arbitrarily, and each time we put the new user at the top of the join tree here.
So your question was?
My question is. Let me how to phrase it. We had some particular user activities like the MBone data. The idea actually is not from me. This idea is from another group member, and he was working. We are working closely together. So the question I had for him is, supposing MBone, some users just join and then they suddenly leave. They join the leave. If you have this line. They join, and then they relocate. And then they leave. All of them leave, one by one. Then the leaving time could be much larger. Because we have a line here, and then when the first one leaves, we relocate all of those. And then all the users relocate the line.
No.
All the line. We relocate. Yeah. We relocate the line into as a small tree here. And then, suppose the small tree users are leaving from the main tree. They all leave from the main tree here. The time class, it's still log n. Still log n. It's not going to have, yeah. So the question I had for this one is, the join part we can also get gains like in this one. This one, we are guaranteed to reduce the average join time by using the join tree. It's very easy to get gain from the join perspective. It's hard to get the gains from the leave perspective, because that's the problem, because it's hard to predict. Yeah. The time goes this way. It doesn't go back that way. So.
As you know, you have like the assumption, one of your assumptions as well. Someone reports and
yeah.
That's accurate. If this is actually true,
yeah.
then you do the same thing. You do a line on the exit tree.
Yeah.
Keep it set, but then it's going to be very sensitive to inaccuracy.
Yeah. So. One of the reviewers for the paper, the conference paper appeared in InfoCom last in March. One of the reviewers' comment is, how practical is this exit tree to the inaccuracy, according to the inaccuracy? So there are several simulation results that I have done after that paper comes out. We are trying to see what are how much inaccuracy we can tolerate, especially in this case.
Okay.
Oh, thank you.
Thanks.
Well,
So,
I better be careful. Otherwise, my next paper will appear from Microsoft Research. I'm kidding. I'm kidding. Yeah. Yeah.
No, I'm glad.
These are these are really smart people. In an hour, less than an hour and a half, they talked to me about my next paper. I never talked to other person.